Let's see, that's section 5.8. Did you practice integration? I'm asking students that are attending live and students that are watching then watching later. Okay, I can hear lots of yes and I can see lots of thumbs up. Okay, thank you, Lara. Okay, that's what we did. Let me come back for a second because we finish the first session about the U substitution, integrating through the U substitution definite integral. Right? That means definite integral means that we have a limits and we can see we also have to change the limits if we pick that method. Yes, we remember everything in terms of U, even the limits. If for some reason you don't want to compute any new limits, you can do this computation like inside. And let's see what we did. I am still using U substitution. I am rewriting everything in terms of U, but I am kind of like ignoring the limits. Yes, do you see? I'm not writing them. I can say possibly just to know that this is still definite integral, I can say U sub 1, U sub 2, U sub 1, U sub 2. But we don't have to, because at that moment when we have the final antiderivative, we can rewrite in terms of x. And as soon as we have in terms of x, we can place the original limits of integration. And then we know what to do. Fundamental theorem of calculus. Substituting upper limit and then substituting lower limit. Okay. Excellent. Let's see. Let's look at this one is relatively easy. This one, maybe this one. Let's try, let's see. Maybe we can compute, yes, new limits. Okay, that's what we have. We see two functions, 2x, and then square root of the quantity x squared plus 5. I believe it's kind of like obvious that we have to at least start with the inner function x squared plus 5. We will let u to be x squared plus 5. Derivative of u is du. Derivative of x squared plus 5 is 2x dx. Actually perfect. 2x dx. That expression, 2x dx, can be replaced with du. That's it. We don't have to play with any coefficient. Okay, that means this is 1 over square root of u, and this is just du. That's it. 2x dx is du. Also, sometimes I see like because you probably learn the U substitution from different sources, from different professors, like from different. And I know that what sometimes students do, you will completely solve for x. Yes, that means you will have du over 2x. And then what you will do, you will substitute. You will copy 2x. You will put square root of u because this is u. And dx is du over 2 root x, and you will cancel out. But I don't really recommend doing this. Like, kind of like mechanically, it's okay because we just getting the same integral. But we remember mathematically, we cannot really put x and u if we only have du. Yes, if you only have one variable function. The same this one, du and x, that doesn't look nice. I know that like fraction-wise, algebraically, arithmetically, it might look correct, but we're not doing this. Okay, that's in, please try, especially on the open-ended question, on the written homework, please do not write this way. Just write the nice, proper way. Okay, and we can nicely see 2x dx can be simply replaced with du. Okay, let's maybe compute the limits of integration. I will just rewrite function 1 over square root of u as a function u to the negative half, but let's just find a new limits of integration. It means when x was 2, then u, the new value, will be that expression x squared plus 5, 2 squared plus 5, 9. And when x is 3, then u will be 3 squared plus 5. What is 3 squared plus 5? 14? I think. 9 plus 5, please check. Yes, thank you. Okay. Let me, okay. Yeah, that's when we can put them from 9 to 14. From 9 to 14. Okay, now we good. Integral of u to the negative half, it will be u to the positive half over half, 2 square root of u. From 9 to 14. Beautiful. 2 square root of 14, 2 square root of 9. And that's we can see, we can substitute them right away. I don't know this one, we can have to keep like this, and this one will be 2 times 3, 6. Yeah, we can. I was planning to factor out 2, but it's fine. Okay, that means that's one way. That's please remember, don't solve completely for dx. Yeah, I know, even if you learn this way, try to unlearn. Okay. Another nice integral, tangent cube theta secant square theta. Yeah, they both look like the inner function, tangent and secant, because tangent is raised to the power of 3, secant is raised to the power of 2. But what we can do, that's we can try u to be tangent theta, that's inner function, or we may eventually try u to be secant theta. Yes? But let's think which one will be helpful. And because both of them are inner function, when I really follow my steps, my guidelines, I will put, yes, I will try this. But what is the derivative of tangent? Because we have to differentiate. Derivative of tangent is secant square theta d theta. Derivative of tangent theta, secant square theta d theta. And now we can see this is du. Derivative of secant theta is secant theta tangent theta d theta. That's we have one tangent will be cancelled out because this one is cube, but then another tangent will stay, and then we also need secant. That's I don't think this will be helpful at this moment. Okay, that means we basically have tangent cube, which this is u cube. Okay, that's it. U to the power of 4 over 4. And what are the new limits of integration? Can somebody help me? Let's say new bounds. That's the same thing. When x is 0, u is basically tangent of 0. And what is tangent at 0? And when x is pi over 4, u is tangent of pi over 4. Tangent at 0 is 0. Okay, that means that's a new 0. And what about tangent at 45? Tangent at 45 is 1. Yes, our best limits of integration from 0 to 1. Okay, 1 and 0. Of course, I could skip 0. 1/4 is the final answer. Really nice limit. But we can see, integral. We can see we have to be a little bit careful because they both look like inner functions. Yeah, but we can see we don't see that part in the integrand. Yes, yeah. However, let me check something. Because if one secant, we could solve it. Yeah, we could, because we have secant square. Interesting. Actually, if we really, let me just put, if we really like, let's say you will decide to do u equals to secant theta, then derivative of secant, because I just want to, is secant theta tangent theta d theta, okay? And let's see how we can rewrite. We can say tangent square theta, because this is cube. We can say secant, and then secant theta tangent theta. Actually, I think it's even possible to solve this way. Sometimes it's not. And of course, we don't have to, just as a practice, as a like, to be really confident that we don't really blindly follow the rules. Okay, that means I still have tangent cube and I still have secant squared. Yes. And now let's see what's happened. That's what we can do. Let's use the red backwards. That means secant is u. Secant tangent theta d theta, this is du. Okay, we're not in bad situation because we are a little bit lucky. This is even power. That's in what we need. I cannot really put tangent square, but if I will rewrite tangent square in terms of secant, what is tangent square theta in terms of secant theta? Do you remember that property? Where can I squeeze? Maybe here. I think it will be tangent square theta plus 1 equals to secant square theta. It's just the Pythagorean identity, but for secant and tangent. That means tangent is secant square theta minus 1. And secant is u with respect to our substitution. Yes, I'm just solving a little bit different. That we can say u squared minus 1. Actually, yes, we can distribute. The integral will be u cubed minus u du. Wow, and we can nicely integrate term by term, and I believe we will get 1/4. Actually, I think we just lucky because if this will be different power than 3, it will be a little bit more complicated or maybe not even possible. But since I took one tangent for the derivative, for the du, we end up with the squared, and we like the squared. It was easy to rewrite, because if this will be cube or any other odd number, it will be not that easy. Okay, also nice way of thinking. I just realized, yes, you can do it this way. But I think this one is more obvious. Let's look at this solution. It's just u cubed and this is du. That's it, because that's the derivative. Yes? Okay, but just in case, we can see that purple rewriting is also correct. Okay, nice, really nice. The same idea, you can try. You can do sine or you can do cosine. I think 1 will be good. Sine looks like an inner function. Another one, secant tangent, even better than the previous one. You can try to do this one. Also, you can like manipulate with the derivatives and identities, trigonometric identities. Let's try. Find the area under the curve, x over x squared plus 1. Because this one will be interesting. Integral, I mean, simple, yeah? From 1 to 3. And we actually can see based on the graph that this function is above the x-axis. That's when we can call it area under the curve, because that's the definition of the integral. It's an area, it's a net area. In this situation, it's actually area because it's positive. Okay, that means the area under, let's maybe put, it's an integral from 1 to 3, just this function. Oh, this is actually 1. Okay, and how we can solve this integral? How we can solve this integral? It's actually interesting. We will talk in a minute about something, because that denominator is really important. X squared plus 1. Or maybe x squared plus 9, x squared plus 16, x squared plus any quantity squared. Or x squared plus any, actually, quantity, positive quantity, because we may always figure out. Okay, but at the moment, we just see x, we see x squared plus 1, and I believe, yes, because this is looks like this one is the inner function because it's sitting in the denominator, yes? That's mean yes? That's actually u substitution. Derivative of u is du, derivative of x squared plus 1 is 2x dx, and we only have x. That means I will divide by 2. X dx can be replaced with 1/2. Yes, Reese, we will talk right away about that integral. Yes. That's mean always when we see this denominator, x squared plus 1, like here, we may follow, like we just follow the u substitution rule, but we always have to think a couple of seconds because it could be the inverse tangent, the arctangent. But let's see the difference when we will apply that direct antiderivative, okay? And when we will be doing what we actually doing here for exercise 16. Okay, that means let's rewrite. We will have denominator is u, x dx, it will be replaced with 1/2 du. We can put 1/2 outside, and it will be just the integral of 1 over u. And what is the integral of 1 over u du? It's just natural log of u. And let's compute a new limits. Okay. New bounds. When x is 1, then u is 1 squared plus 1. I'm using that formula. 2. When x is 3, because we are from 1 to 3, u is 3 squared plus 1, 10. Am I right? Yes. From 2 to 10. And I can put these values wherever I had u. Okay, that's we have the final answer. 1/2 natural log of 10 minus natural log of 2. Since this is parenthesis, we may divide, because when we subtract the same logarithms, the same base, we can divide the arguments. Okay, 1/2 natural log of 5. Or natural log of square root of 5, because we may apply as a power, and 5 to the 1/2 is square root. But no, the first option is it's better. Okay, really nice, really nice. Okay, that's it. Now let's actually look at this integral. X squared 1 over x squared plus 1. That's me. Let's see. Yes, that's actually perfect. Let's look at this. First of all, we have to know that's the differentiation, that's the integration formulas. Okay, that's direct, that's almost direct, because we can actually say 1 over ln of a is constant, and integral of 1 over x is natural log of x. Okay, and if we change the base for the logarithm, we will have that formula. That means this one is even better. Okay, the first one is direct. The second one, the second one is actually the u substitution. Yeah, that's we may notice it's when we have a rational function, and you probably notice even the previous one. When you see the function in the denominator, like for instance, 1 over sine of x, we cannot really say natural log of sine of x. No. We may, because that's too much. The chain rule, the cosine is missing. But if I will put cosine of x, that means if we think about the u substitution, u will be sine of x, du is cosine x dx. That's we will end up with 1 over u du. Then it's correct. Then it's correct. That means in general, when we have rational function and you see denominator and its derivative on the top in the numerator, we can all, if you like, we can say right away natural log of the denominator. That's it. Or you can, of course, do the substitution. This will be u and this will be du. 1 over u, integral of 1 over u, natural log of u. And this was u. Okay, that means this one is just the u substitution with logarithmic expression. Okay. Now we have this formula, of course, power rule. We remember. This is just the reminder, just the power rule. But when n is -1, then we have 1 over x. And the answer is natural log. We just did it, yes, but I'm just reminding this. And then we can reverse all of the inverse trigonometrics. But I don't know, we don't worry for those. And even cosine. Cosine is just negative. What I really would like you to remember is arcsine and arctangent. Yes, that's the same like arcsine of x, arctangent of x. Derivative, and then the integral. Arcsine of x and arctan of x. That's now we can see that denominator. And what is important, when you see this integral, yes, 1 over x squared plus 1, of course is arctangent of x because derivative of arctangent is this. But please notice the difference that I was just saying for the last exercise. Actually, what is the difference? This integral is 1 over x squared plus 1 dx. And we know the answer, arctangent. The integral that we just solved, it also had x squared plus 1, but had x on the top. That means, do you see the difference? This is like variable. It's another function. When we have constant on the top and you still see this nice denominator, then yes, it will be arctangent. Constant, nothing, like 1, 2, 3, -1, any non-zero constant. But when we have variables, then it will be probably different answer. Could be, maybe partially will be arctangent, but definitely we have to look at something like different, like u substitution. That means please be careful, yes? We cannot say right away that this is, that's the worst, x times arctangent. No, we have to integrate this as a whole. Okay, that's means please remember. And also this one, also please be really mindful when you see this denominator, I'm repeating this, it's arctangent. Because what is the common mistake for this integral? Natural log of the denominator. We cannot say natural log of the denominator if we don't see derivative on the top, because that derivative is the part of the u substitution. Okay, that's it, please. Yeah, that's the main difference. Okay, what else? Let me just, this one will be super easy, just natural log, super easy. What about this one? Let's do this one. This one is a little bit different. Natural log of x over x. We will reach the arctangent in a minute. What substitution we can do? From 1 to e looks like function is positive. That means looks like we're calculating that area. But the point is to calculate it. We can definitely say natural log of x. Because what is the derivative? From 1 to e, we have natural log of x times 1 over x dx. 1 over x dx. That means du is just 1 over x dx. This is u, and this is du. Done. U squared over 2. Can you tell me the new limits of integration? New bounds. When x is 1, then u. When x is e, then u has the value. Yes, and what is, yes, we using natural, that's the natural log of 1, natural log of e. What's natural log of e is 1. What about natural log of 1? Natural log of, any log of 1 is 0, because e to the power of 0 is 1. Okay, that's we have from 0 to 1. Again, the most wanted limits of integration, because that's the easiest one. Okay, 1/2 is the final answer. Right? Really nice, we can see. But always try the U substitution, and try to practice. You will like it. You will really like it. You will feel so satisfied. Okay. That's the formula. That means when we may use the U substitution, but sometimes it's nice to figure out when we see rational function in the denominator and its derivative is on the top, then this integral is natural log of the function from the denominator. Basically, it is when we will let u to be that function, then derivative of u is f prime of x dx. That we can see f prime of x dx. This is du. Then the integral will be 1 over u du, natural log of u. And u, of course, was f of x. That means I hope we can see this. Then we know right away that we can say natural log of the denominator only if you see derivative on the top. That means, for instance, this one. What is the integral? 1 over x plus 1. This one is x plus 1. Natural log of x plus 1. Just because derivative of x plus 1 is 1. What about this one? 3x squared minus 1. But what we see on the top? Derivative. Natural log of the denominator. Perfect. And what about number 3? Crazy one. We don't have to be worried. We can say, derivative of tangent is sitting in the numerator. Derivative of e to the x. Then natural log of the function from the denominator. Perfect. Okay, just in case I like to show you these shortcuts. Okay, number 5. I can leave it for you. The only thing is, we see the squared. That's when we see the product. Okay, that's in, please, remember, we cannot really integrate that term, this term, and then take the square of that integral. That will be not true. We have to expand the form. That means let's FOIL e squared e to the e to the x plus e to the negative x times e to the x e to the negative x. And then when we FOIL, it will be e x squared 2 times e to the x e to the negative x, and then e to the negative 2x. Yes, when you FOIL, you will have this. And then one more. This one will cancel out, and this one. Okay, and we know the antiderivatives. I can just say e to the ax dx is e to the ax over a plus the constant. And that's when we remember like how this linear coefficients can affect the graph. Okay, antiderivatives also. Okay, we good with this one. You will be good with this one. I just want to, inner function and everything is cancel out. Even easier. Inner function and everything will be cancel out. We just did number one. Let's do this one. Because where is my arctangent? Arctangent. Okay, nice exam type question. Okay, how would you solve this integral? Sine of x over 2 minus cosine of x. Interesting. We can do u substitution, or if you remember what I just said, you can tell me the antiderivative right away. But we may do the u substitution. We have no choice, yes, and we're actually lucky because the only technique that we know is a u substitution. In Calc 2 will be more challenge because we will have different techniques and we have to decide which one to use. Yeah, I think function from the denominator has its derivative on the top. Yeah, that means this is du, this is u. 1 over u du. We could even skip this natural log of u. We just need a new limits of integration. Okay? Or we can come back to the original variables 2 minus cosine x and use 0 and pi. But we can use the new one. Okay, what are the new bounds, new limits? When x is 0, then what is u? When x is pi, what is the another u? We're using this. 2 times minus cosine of 0. What is cosine of 0? Cosine at 0 is 1. Yes, thank you. 2 minus 1, it is 1. That means this one is 1, 1. What about 2 minus cosine of pi? Cosine at pi, it's negative 1. Subtracting negative is adding 1. 2 plus 1, 3. Okay, perfect. Natural log of 3, natural log of 1. We may divide or we may just say this, since natural log at 1 is 0. Okay, beautiful. Yeah, we can see how nice and easy will be final test. Okay, let's look at this one. You can do it because you see the derivatives. Oh, okay. This one. Okay, let's look at this one. Because what we know, we definitely know, I can probably give you the formula. We know this, that means this one is x squared plus 1 dx. Arc tangent of x. That means now let's play. Okay, this one will be definitely arc tangent because it's no variable on the top. And we just have x squared plus, instead of 1, we have 4. That 4 affects, yes, that 4 affects the arc tangent, but the main thing is it is arc tangent. And how I can provide this as a formula, x squared plus a squared, which in our situation is 2 squared. How that quantity a affects. But before let's actually see. Let's maybe solve this one. Let's say we don't remember the formula, okay? Actually, let me provide the formula because we will use this formula for sure, just to simplify. If we see integral like this, you will, yes, do it. And then we will actually prove based on this, because we will use the u substitution, that the formula is correct. Okay, that's we have x squared plus a squared. This is still arctangent, but x will be divided by a, an entire arctangent will be divided by a. So we can see how x is divided by that quantity a and 1 over a, entire arctangent. Okay, that means the final answer for this one will be arctangent of x over 2, 1/2. Okay, done. But let's actually do it. What we can do. How we can get that? Because this is direct. This is the direct antiderivative. That's the formula. That's what I like. I like to see quantity squared plus 1. That means maybe we don't like this 4. I will factor out 4 and we will have 1 plus x squared over 4. Simple. Correct? Now we will have 1/4 outside. We have 1 plus, and the only thing that we have to rewrite a little bit, we have to combine this. I have to have an inner quantity squared. That means x over 2. Makes sense? Because x over 2, the entire quantity squared, results in x squared over 4. We're squaring x and we're squaring 2. X squared over 4. And now I can actually use this as an inner function and do the u substitution. Derivative of u is 1/2 dx, 2 du equals to dx, because we don't have 1/2. I mean, we have 1/4, but we keep it outside. Okay, 1/4. And now, let's actually put, it will be 1 plus u squared, because the quantity inside, and dx is 2 du. Yes, 2 du. That 2. 2 du. Okay, 1/2, I mean 1/4 times 2 is 1/2. 1 plus u squared du. And we have 1/2, and this integral is just arctangent of u. Arctangent of u, which actually u, we can come back and rewrite like x over 2, the original verb. Okay? Yes, we can see if that's where all of these coefficients come from. But we don't have to spend time on this basic, actually, yes, integral. You may always identify, okay, this is 4, then it will be 1/2 x over 2, still arctangent. Okay? So now let me maybe ask you. Okay, everybody now is thinking, and what are, okay, number 1, integral of x squared plus 9 dx. Can you tell me what is the answer? X squared plus 64. Okay, what is this, the first one? It is arctangent. It is arctangent, but the first one is 1/3 x over 3. Thank you. Yes, yes, really good. Okay, oh, inverse tangent, of course. And what about the second one? Arctangent of x over what quantity? Square root of 8. Thank you. 8. Yes. Okay. Okay, that's we good. Yes, we good with this. And for instance, I mean this one, let me put quantity squared plus 1. Yes, because that will be another option for arctangent, but the u substitution. I mean, this one is the also u substitution, but it's constant. But what we may have theoretically any quantity squared, any. Yes, and then I can say, if this is 1, then we don't have this extra coefficient. Arctangent of this quantity, yes, any quantity. However, if I put any quantity, like, I don't know, I can even put tangent of x. Then in order to say this, because theoretically I will let tangent of x be the u, I need du, I need derivative. That means if you have any quantity squared plus 1, then we have to think it could be arctangent, but what we have to see the derivative. Then yes, this is arctangent of tangent x. Probably we can make some simplification, but if we will not have that derivative, then it will be not true. Then we have to figure out something different. Okay, that means now we have to be really like careful. We have to pay attention. For instance, this one, when we see in the denominator quantity squared plus 1. Okay, sometimes we can grab the entire quantity and let u to be this quantity. But I think we have to be careful because usually, yeah, it could be too much, the entire quantity. But we see, yes, this is also important. 1 plus quantity squared. Okay, and we have to think possibly it's an arctangent of this quantity. Quantity is cosine, and we actually see on the top sine. That means this will work. U is cosine of x. Derivative of u is negative sine of x dx. Negative du is sine of x dx. Beautiful. So I can say 1 plus u squared, and sine of x dx is negative du. Actually, that negative can go. Okay. Negative, oh, too fast. Negative arctangent of u. Yeah, which is arctangent of cosine, of course. Oh, we have a limits of integration. Let's find the new limits. But we can see that's also important. Always we paying attention when we see quantity squared. Okay, new limits. Please give me the new limits, new bounds or new limits of integration. When x is 0, u is cosine of 0. When x is pi over 2, oh, my pen, oh, I cannot erase, not good sign. U will be cosine at pi over 2. Cosine at 0, 1. Cosine at pi over 2, oh, actually 0. That's we have from 1 to 0, from 1 to 0. If we switch the limits of integration from 0 to 1, this will be opposite sign, positive. Yes. Oh, that's what I thought. Something is not good. This sometimes behaves. Okay. From 1 to 0, we had it, right? Then I can switch arctangent of u from 0 to 1, because when you're switching, then the opposite. Okay, just arctangent of 1 minus arctan at 0. What is arctangent at 1? Tangent for what angle is 1? Pi over 4. Thank you for helping. Okay, I will not rewrite this. You can find the new limits. Okay, that's in. Please, yeah, please be really careful. Okay, what else? Let me check. Another quantity squared. 1 plus quantity squared. Okay, 1 plus quantity squared. And the quantity is e to the x. You may try the u substitution. Oh, that's maybe, yeah, this one is a little bit tricky, because this one is actually, I would say, it's nice integral, actually, really nice, but it looks a little bit like calc 2, or maybe not, because what we have to do, oh, do you see something is, let me keep this. And let me do this. Oh, of course, I lost that. I knew it that something is wrong. Okay, let's maybe what we have. All of them are relatively easy. I would like to show you this one because this one has x squared plus 16. That means we kind of know what this denominator is telling us. We have 4, like coefficient 4 will be 1/4, will be affecting, looks like arctangent, but we have variable on the top. And not even that, we even have expanded form. That means different situation is happening when it's constant on the top of that denominator and when it's the variable on the top. That means what we can do. We can basically, since we know that we have to behave differently, we can split this. I mean, that's what I was saying, that this is maybe tricky, maybe not. And now, so obvious. What is this integral? What is this? Actually, let me maybe apply one more property that we're using, because we will just integrate this minus integral of this. I will just split. Okay, that means this integral is arctangent because it's constant on the top. X is affected by 1/4 and the function is affected. Okay, minus, that's we have that part. And we will, of course, subtract. What about this one? How would you solve this integral? I think that's a nice example maybe to finish the session. Because now u substitution. Yes? When we will let u to be denominator, x squared plus 16, derivative of x squared, yes, is 2x. That means it will be 1 over u du, natural log of u, and this is u. Okay, that's we can see how two different outputs, two different antiderivatives for the same denominator, but different numerators. Really good. Okay, that's it. Let's finish. Let's remember that little trick that we can split and take care of both of them. It will separately. It's helpful now, of course, to think a little bit different, and definitely helpful in Calc 2, Calc 3, differential equations, entire journey of your journey with mathematics. Okay, that's it. Thank you. We can finish. I still have more integrals, but we can, you can try. I solved all of them. That's it. Please look at the blank presentation without the solution. Try to go integral by integral, because if you integrate more and more, you will feel confident and then you will feel better. Everything will be better. Okay, that's everything for chapter 5. Next week, we will do a little bit of applications. Areas between two curves. No, you mean the final exam. Final exam will actually be cumulative. That means we have to cover everything, but probably 50% of the test will be chapter 5 and 6. Because these materials were not tested on the midterms. Okay, that means half of the test, or maybe even 60%, it will be integration, yes, application, integration, yes, and the other 40% or maybe 50% will be the old material. Yeah, actually, yes, 25% from the first midterm, 25% from the second midterm, and 50% the material after second midterm, which is chapter 5 and 6. Okay, that's me. Next week we will just do area, like between two curves. That's me. This will be like an application. Area, volume, and work. 3 questions. You have to know how to compute the area between two curves, volume of some solids, and work. Yes, work that is different. Yes, different work and force. Different, like, yes, forces are applied at the certain moment. Okay, because when it's linear, when it's not constant force, then it's not a problem. But yes, when it's different, we have to look at everything. For instance, like if we have to, how much work is done when the bucket of water is like hanging on the chain in the big hole, and we have to pull it up. That's when it's lower, it's heavier for us. But when it's going, when the distance, and also the chain weights. Yeah, that's when also the chain, even the heavy chain without any bucket. Yes. Then we will, yes, then we will. Oh, let me, yes. Okay, that's just, yeah, that will be chapter 6. Okay, I'm just talking too much. We will do this next week. Thank you, and please enjoy your integration. Lots of integration. Okay, thank you, and see you next week. Thank you.